Hi, my name is Farah. In this video, I will solve the chemistry assignment question on the screen. Here are some topics we are going to cover. Let's begin with the first question. This is our first problem. This problem asks us to determine the shape and bond angles of ammonium ion NH4. As you can see here, I am drawing the Lewis structure based on the outermost electrons of each atom. Nitrogen is bonded to 3 hydrogen atoms and has one pair of lone electrons above it. However, when it reacts with an H plus ion to form the NH4 plus, that lone pair of electron is used to form a new bond with the fourth hydrogen atom. According to VS-EPR theory, when a central atom has 4 pairs of bonds, it forms a tetrahedral structure with bond angles of exactly 109.5 degrees. The next question asks about what is the enthalpy change of neutralization of hydrochloric acid? Here, we know that the total volume is 50 milliliters, the mass is 50 grams, and the temperature change is 15 Kelvin. We plug these values into the formula Q equals to mc delta T, and after substituting all two values, we get a result of 3,135 joules, which we convert to kilojoules to get 3.135 kilojoule. Next, we find the numbers of moles of water, which is 0.1 mole. In the final step, we substitute the negative heat energy per mole of water and obtain the final answer, which is minus 31.4 kilojoule mole to the power of minus 1. Moving on, we need to find the value for the standard enthalpy change of combustion of ethane. When you are given combustion data, the formula is the enthalpy change of formation equals the total combustion of the reactants minus the total combustion of the products. Here, I have written the chemical equation for ethane so that we can clearly see the reactants and the products. So our equation now look like this. Negative 140 equals negative 1945 minus x. X equals to negative 1509 kilojoules per mole. Here's our next question. Just like the last question, since we are dealing entirely with combustion data, we use our trusty Hess law shortcut, reactants minus products. We'll just plug the values from the table, do the math, and we get the final answer of negative 134.5 kilojoules per mole. The student calculated the formation of ethane to be negative 158, but he used a wrong combustion value for carbon. We need to find that wrong number. Since it's combustion data, use the rule reactants minus product. That leaves us with negative 158 equals 2x plus 702, and x equals negative 430. Moving on, we need the correct reaction graph for converting x into z through intermediate y. First, since intermediate y can be isolated, it must sit in a valley between two peaks eliminating b and c. Next, step 1 has a positive delta h, so y must be higher up on the energy axis than x. Step 2 has a negative delta h, so z must be lower down than y. Moving on, we need to find the overall enthalpy change for equation 1 using 3 given stages. To get equation 1, we must adjust the coefficient of each stage to match our target reaction. First, multiply stage 1 by 1/4 to get 1 mole of ammonia. Next, multiply stage 2 by 1/2 to cancel out the nitrogen monoxide. Then, multiply stage 3 by 1/4 to get 1 mole of nitric acid. Finally, add all 3 modified delta H values together. Negative 226 plus negative 57 plus negative 87 equals negative 370. The question asks to find standard enthalpy change of formation for methanol. We are given entirely combustion data, so write down our shortcut rule, reactants minus products. To form 1 mole of methanol, our reactants are 1 mole of solid carbon and 2 moles of hydrogen gas. Our product is simply 1 mole of methanol. Now, just substitute the values from the text directly into our formula. That gives us 1 times negative 398 plus 2 times negative 286 minus negative 726. We need to find the enthalpy change of combustion for ethene. When using bond energies, our formula is always reactants minus products. That means bonds broken minus bonds formed. Let's count the bonds on the reactant side. We break 2 CH bonds, 1 C triple bond C, and 2.5 O double bond O. Total energy equals 2,900. Now, for the product side, we form 2 OH bonds in water and 4 C double bonds O in carbon dioxide. Total energy equals 3,880. Now, just do the reactants minus product. That gives us exactly negative 980. Moving on, we need to calculate the enthalpy change of neutralization per mole of sodium hydroxide. Because the unit uses centimeters cubed, our formula automatically changes from mass to volume. So, we just take our total volume of 50 cubic centimeters, multiply it by 4.18, and we can solve for delta T to get 522.5 joules perfectly without converting to grams. Now, calculate the number of moles of sodium hydroxide and get 0.0025 moles. Finally, divide 522.5 joules by 0.0025 moles. This gives negative 209,000 joules per mole, which converts to negative 209 kilojoules per mole. Moving on, we need to find the correct statement about the two sulfur dioxide reactions. According to the Bronsted-Lowry theory, a base is defined as a proton acceptor that takes in an H plus ion. If we look at the first reaction from right to left, the hydrogen sulfide ion accepts a proton to turn back into water and sulfur dioxide. Because it acts as a proton acceptor in this reverse step, HSO3- is acting as a base. This makes statement A the correct choice. Moving on, we need to find the reaction where ammonia behaves as Bronsted-Lowry base. By definition, a Bronsted-Lowry base must accept a proton, which means it has to take in an H plus ion. If we look closely at option B, the ammonia molecule NH3 accepts an H plus ion to turn into the ammonium ion NH4 plus. Because it gains a proton to form this new ion, ammonia is acting as a base in this specific reaction. This makes option B the correct answer. Moving on, we need to find the correct statements explaining these four pH values. Statement 1 is incorrect because nitric acid has a lower pH due to being a strong acid, not because of its solubility. Statement 2 is correct because sodium hydroxide has a higher pH of 14, meaning it dissociates completely to release more hydroxide ions. Statement 3 is also correct because ethanoic acid is weak acid that dissociates less than nitric acid. Since statement 2 and 3 are correct, option C is our final answer. Moving on, the question asks us to find which mixture will react to form exactly 1 mole of water. To figure this out, first I will write down the balance equation on the right side. Acid plus 2 alkali produces salt plus 2 water. This gives us our base mole ratios. Looking at the coefficients, both alkali and water have a value of 2, so I can write water equals moles of alkali, which gives us a simple 1:1 ratio. For the acid, water has a coefficient of 2, which is double the acid's coefficient of 1, so I will write that water equals 2 mole acid, showing a 1:2 ratio. Now, let's quickly test the option to find our match. For option A, the acid is 0.5 moles and the alkali is 0.5 moles. The alkali limits the reaction, so it only forms 0.5 moles of water. For option B, the acid is 0.5 mole and the alkali is 1 mole. This hit our target ratio perfectly, producing exactly 1 mole of water with 0 leftover. Moving on to paper 2, so the question asks us to identify what is meant by the shorthand symbol argon in square brackets by giving its full electronic configuration. Now, looking at the periodic table, argon is a noble gas with an atomic number of 18. This means a natural argon atom has exactly 18 electrons that we need to arrange into subshells. So, the full electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Moving on, we need to calculate the relative isotopic mass of third isotope of iron in this sample. Now, let's plug all our data into the relative atomic mass formula. The question gives us the total AR as 55.8. Since the total must be 100%, I will subtract the other two abundances from 100. That gives us 2.1% for our third isotope. Divide both sides by 2.1 and we find that x equals 56.9. So our relative isotopic mass is 56.9. Moving on to part B, we need to deduce the number of pairs of electrons in the 3D subshell for an iron 2 ion. To do this clearly, first I will write down the full electronic configuration for a neutral iron atom with 26 electrons. Now, the iron 2 plus ion means it loses 2 electrons. This leaves us exactly 6 electrons in the 3D subshells. Since a D subshell has 5 orbitals, these 6 electrons will fill them one by one first, leaving only one pair of electrons. Moving on to part C, we need to sketch the shape of the lowest energy orbital in the shell where the principal quantum number n equals 2. In the second shell, we have two types of subshell, 2s and 2p. Between them, the 2s subshell always has the lower energy level. Since all s orbitals are spherical, I will represent this three-dimensional sphere by drawing a simple perfect circle. Moving on, we need to complete table 4.1 by writing the standard enthalpy change of formation equation for iron 3 oxide and carbon monoxide. Remember, the golden rule for formation, we must make exactly 1 mole of the product, so its coefficient on the right side must always be 1. Let's start with the first row. On the right side, I will write our product produces Fe2O3 solid. Now, moving to the left, what elements make this up? Solid iron and oxygen gas. To balance them out, I will add 2 Fe solid plus 3/2 O2 gas. For the second row, I'll do the exact same thing. On the right, I'll write the product produces CO gas. Moving over to the left side, the elements are solid carbon and oxygen gas. To balance it perfectly, I'll write C solid plus 1/2 O2 gas. And that brings us to the end of this chemistry worksheet. We've covered everything from electron configurations and orbital shapes to calculating enthalpies using Hess's law. Hopefully, this step-by-step breakdown gives you all the confidence you need to do amazingly well on your upcoming chemistry exam. Thank you so much for watching.